Morning, class. Can you guys hear?
Yes, sir.
Yes, sir.
You can see the screen as well.
Yes.
So hopefully you guys had a good semester break. Are back and ready to work. Okay. All right. So today we're going to be covering some stuff on circular motion, which is just motion in a circular path. But because it's in a circular path, certain things are a bit different. And we have some background in things like angular velocity and angular acceleration. So that will help us a little bit when approaching these problems, right? So let's just get right into it.
Sir, you should plug in your charger for us.
Okay, so charging. Okay, so now there's some formulas we need to pick up and I'll go through them briefly along the way, right? But let's just start straight away with the question so we can see how we apply them practically instead of just trying to learn a lot of theory. Okay, so number 19, a ball is suspended from a string attached to a swivel joint and revolves in a horizontal circular path with a constant angular velocity. Show that the vertical height from the center of the ball to the point of suspension is independent of the length of the string, right? Independent of the length of the string. We need to show that vertical height is independent of the length of the string. If the ball has a mass of 1 kg and revolves at 50 revolutions per minute at the end of the string, 1 meter long, find the tension in the string. All right, just give me a few seconds. Okay, I'm back. All right, so what you guys would have gone over with Mrs. Sill is probably this formula here. That the centripetal force, right? The centripetal force required to make the mass travel in a circular path is M is equal to M, where M is the mass, times omega squared times R. Now, what is this centripetal force? Let's say we just had some point in the middle of a desk or something. Then there was some cord or some arm, and attached to that was a mass. It's a mass with the mass M. Now, as this thing spins around, okay, in order for it to move in this circular path, there needs to be a force pulling it into the center. Right? This force is called the centripetal force. Centripetal. Now, another word you might hear is the centrifugal force. Now, we know that forces have equal and opposite reactions, right? If there's some force pulling this thing into the center, towards the center, centripetal, petal meaning towards the center, there must also be a force pulling on the pivot point, leading outwards, right? Called the centrifugal force. Okay. Centrifugal. Fugal force. So that's what the centripetal force is the force pulling the mass inward, keeping it this way, right? Now, let's say this object is moving at some velocity. Let's say it's going around this way. Some linear velocity, and that linear velocity would be tangential to this circle. right? Going out. V. V. Now, in order for it to change, this velocity needs to be constantly changing from here to somewhere like, to something like this as it moves around, right? Something like this as it moves around. So the linear velocity is constantly changing. And the reason it's changing, right? Its magnitude is going to remain the same, but its direction is going to be changing, right? Its direction is going to be going around along the circle, tangential to the circle, tangential to the circle, right? So in order to get that change in velocity, we need some kind of acceleration, right? We need to accelerate it in a different way, right? So velocity here, let's say we have velocity going this way, that's 4, right? 4 meters per second. In order to make it go the other way, right? This way, even at that same magnitude, right? We need to accelerate it in a different direction, right? So all along here, we have some acceleration, right? Now, acceleration, we know, is only comes about from some force, right? We need to apply a force in order to get acceleration. And that force comes from this cord or this string or this arm pulling this mass back into the center. And now in the handout, did a little bit of math, and they found out that acceleration is omega squared r. Omega squared r. And that's the formula for centripetal force. Now you can go ahead, you can have a look at the handout and learn all about the intricacies of this formula. But it's essentially an extension on F is equal to ma, where a is that acceleration from the centripetal force that we characterize as omega squared r, right? So F is equal to omega squared r. Now, this system with the ball suspended from a string attached to a swivel joint rotates in a horizontal circular path represents a conical pendulum, right? So a pendulum, a conical pendulum, so it's like this, some string attached to some point on your ceiling, perhaps. Then on that is some mass, let's say mass M again, right? Mass M is going to rotate in a horizontal circular path, okay, like this, creating the shape of a cone. So imagine this line, right, going around this circle, this horizontal circular path, creating a cone. That's why we call this machine a conical pendulum, because it creates this cone, right? Now, if you were to take different moments in time of this, we'd see some forces being up here, right? Now, there's obviously the tension on this string, right? There's some tension pulling this thing back in, right? And then there's the equal and opposite reactions and whatnot. We can just call that tension T. Now, this tension T can be broken up into two parts. One part is here, right? Let's call this some angle here. The angle that it makes with the horizontal, theta, right? Let's call the angle that it makes with the vertical, sorry, theta. Angle with vertical is theta, right? Now, this horizontal component of T is going to be T sine theta. And that's equal to the centripetal force, right? The force pulling on this object back in. Now, there's another force acting on the system as well, and that's gravity, right? So the vertical component of this force, we can always add gravity here because we know, right? Force parallelograms and force rectangles and whatnot, different resultants. We can just as easily put that over here, right? So T cosine theta is going to be equal to the force induced on the mass by gravity, right? Which is just m by g. And this one here is the centripetal force, which is m omega squared r. Very good. Now using these two, we can easily find some formula that says that height is independent of mass of the ball or length of the string or radius of rotation or anything like that, right? How we do that is just by manipulating these two formulas that we kind of created here. So we have these two formulas, and I've rewritten them here and here. So now we know that sine of theta divided by cosine of theta is equal to tan theta. Now, if you didn't know this before, well, now you do, right? Sine theta divided by cosine of theta is equal to tan theta, right? So tan theta here would be equal to this divided by this, right? And certain things are going to cancel out, right? The t is going to cancel out with this t. This m is going to cancel out with that m, right? So what we're going to be left with is sine theta over cosine theta, or tan theta, is equal to omega squared r divided by g, omega squared r divided by g. Additionally, from our little force triangle that we had here with the pendulum, right, the mass here, we knew that tan theta is also equal to r divided by h, right? Opposite over adjacent. R divided by h. Tan theta is equal to r divided by h. So if this is tan theta and this is tan theta as well, then we can equate the two. Yeah? Equating the two, we get r upon h is equal to this thing we just found, right? Omega squared r divided by g. Omega squared r divided by g. Manipulating this, solving for h, we get h is equal to g divided by omega squared, right? We flip this, right? G goes on top. The r's cancel out because when we take this one over, it's going to multiply and cancel with this r, right? And that's it. So just remove this, is 1, r comes here, cancel out, 1 upon h, omega squared g, flip, right? H is equal to g divided by omega squared. And in this formula, we see h is dependent on two variables. Those two variables are g, the gravitational constant, and omega, the angular velocity, right? It doesn't depend on anything else. It doesn't depend on the radius, or which is dependent on the length of the string. It doesn't depend on the mass of the object or anything else. The only two things it depends on is gravity and the velocity at which it's rotating. Okay, so that should prove the first part of the question. Show that the vertical height from the center of the ball to the point of suspension is independent of the length of the string. If the ball has a mass of 1 kg and revolves at 50 revolutions per minute at the end of the string 1 meter long, find the tension in the string. Okay, good. So this thing revolves at 50 revs per minute. 50 revs per minute. Now, converting this into radians per second, which would require us to multiply by 2 pi. Remember, rev to rats, multiply by 2 pi. And minutes to seconds, right? Divide by 60. Right, so multiply 50 by 2 pi. We have 100 pi divided by 60 should give us 5.236 radians per second. And this is the same 50 revs per minute, but expressed in radians per second. Now using this with the formulas we already had, we can find tension. Agreed? So the length of the cord the length of the string is 1 meter long. Right? 1 meter long. Now, for this formula, T is equal to sine theta m omega squared r. Right? We're trying to find T. Right? We're trying to find T. We know mass. We just converted omega here, but we don't know r. So we have two unknowns, T and r. So we need to find r first before we can find T. How we find r is by using some trigonometry. So here, the length of the string is 1 meter long, right? 1 meter. So from here to here, theta is here, r is here. The length of the string is 1 meter long. So that's the hypotenuse, right? Sine theta is equal to opposite r over the hypotenuse, which is 1. So r is just going to be 1 sine theta, or the length of this string sine theta. So we can write it like that, generalizing the formula, so that when we do it in other questions, we know r is equal to L sine theta for these particular systems. So you can remember this as just a quick way. Right? Good. So plugging those values in. T, our unknown, sine theta, okay. M is 1 kg, which was given by the question. Omega is 5.236, which we just converted, right? We're going to square that, and then we're going to multiply that by 1 sine theta. Now there's a sine theta here, and there's a sine theta here, so we can go ahead and cancel those. And then we can plug the rest of this formula into our calculators. 1 by 1 is just 1, right? So T is equal to 5.236 squared. 5.236 squared is 27.416 newtons. And that's the tension. Okay. Okay. Any questions on this so far?
None for me, sir.
None to sleep either. Okay.
Sir, just one question.
Go ahead.
In this case, we had here that h was equal to 1. That is why you used sine theta and 1 sine theta. So they could
Not h, right? H is this height here.
Hypotenuse, right?
Yeah, 1. Yeah, the length of the string was 1. Yeah, the hypotenuse, yes. Good,
So,
and that's why we use 1.
So, if
So
that
this
wasn't
here,
the case,
when the length of the string changes, let's say the length of the string was 2 meters, then you would do 2 sine theta. Length of the string is 1.75 meters. You do 1.75 sine theta. Okay?
all right, gotcha.
So we replace this one with whatever the length of that string is. Right? Or sometimes in some previous working, some working before, right? The question might ask different things. You might already have a value for R, so you can go ahead and plug that value in right away if you already have it. Right? Now, for completion's sake, I don't think the question asks for this, but I saw Mrs. O put it in, so maybe I can put it in. And we can always say that the tension T, if you want to represent it as a vector, is 27.416 newtons applied at some angle theta. Right? Theta to the vertical. Good. So we can just go ahead and find theta really quick. We know M is 1, gravity is 9.81, right? 1 times 9.81 is just 9.81. Tension we just found is 27.416, right? Solving this for theta, we get cosine inverse of 9.81 divided by 27.416 is equal to 69.03, right? Theta is equal to 69.03, approximately 70 degrees, right? So we can say this tension, for completion's sake, right, is applied at 70 degrees to the vertical. right? Because that's what theta is. Theta is here. So let's just move on to the next question. Right? And then I'll give you guys one to work after this so you can practice your skills. Okay. So again, they ask us to deduce an expression for the height of a conical pendulum when rotating at an angular speed of omega rads per second. So they didn't give us rads per second, they just give us omega. And they ask us to deduce some expression for height when rotating at this angular speed. Now we did that just now in the previous question. So you can go ahead and do that back if you want to practice developing this formula. But you can just as easy just write it back, right? And that's the expression for height of a conical pendulum when rotating at some omega rads per second. Now for the actual working. The arm of a simple conical pendulum is 0.6 meters, right? 0.6. Now, just now, the arm or the length of the string was 1 meter, right? So we can see how this is going to start affecting our question right away. Right? Okay. So the arm of a simple conical pendulum is 0.6 meters. And the pendulum bob has a mass of 1.4 kilograms. Determine the height of the pendulum and the tension in the arm when rotating at 75 revs per minute. What increase in speed in revolutions per minute is necessary to reduce the height by 10%? Neglect the mass of the arm. Okay, so let's first analyze this question. So first, I want us to determine the height of the pendulum and tension when rotating at 75 revs per minute. This is something we just did, right? Or we can do using this formula and the similar calculations that we just did. All right, now this next part. What increase in speed in revolutions per minute is necessary to reduce the height by 10%? So what's going to happen? It's here. Let's just draw a conical pendulum, right, with our mass. Now this height here, from here to here, let's call it h. Now, as this thing spins faster, right, this mass is going to come out a bit more, right? As it comes out a bit more, the height is going to be reduced, right? There's going to become some delta h, right? Delta h, and this here is going to become h minus this delta h, right? So what this question is asking is, what increasing speed, how much more do we have to increase it to cause this 10% reduction in the height, right? Cause this height to shrink. Okay. So first, we just want to find basic height and basic tension. So h is equal to g divided by omega squared. Converting omega squared from 75 revs per minute, right? Revs per minute, multiply by 2 pi, divide by 60, we get rads per second. Plug this into a calculator, we get omega is equal to 7.854 rads per second, right? Rads per second, not revs per minute anymore. Okay. We know G is 9.81. That's the constant we use all the time. Plug this now into a calculator, right? 9.81 divided by 7.854 squared. Remember, don't forget to square. Very common mistake. After we finish plugging this into the calculator, we should get h is equal to 0.159 meters, or approximately 0.16 meters. And that's it. That's all for the height. Now for the tension, right? We can go about it pretty similar to how we did last time. We know T cosine theta is equal to mg, right? M is equal to 1.4 kilograms. G is equal to 9.81, right? Now cosine theta. Let's draw our pendulum again. Draw our pendulum again. Right? This is just the pendulum. Now, the arm of the simple conical pendulum is 0.6. right? We just found height. We just found height as being 0.16 or 0.159. 0.159. Now theta or cosine theta, right? Remember here is the opposite, so this here is the opposite. So this here is going to be the adjacent, right? So cosine theta is equal to 0.159 divided by 0.6, right? So we can substitute this in for cosine theta, right? Now, after we put this in for cosine theta, right? We have this in, plug it into the calculator, break it down, multiply these two, right? 1.4 times 9.81 should give us 13.734. 0.159 divided by 0.6 should give us 0.265. Simplifying that should give us T is equal to 51.83 newtons. Now, you can just as easily go about finding tension using the other formula, right? Using this formula we had just now. Just make sure you have enough unknowns. And then you do 0.6 sine theta, and you should get the same answer. Okay, yeah.
So we were not supposed to for the 0.159 divided by the 0. We're not actually not, yeah, we're not supposed to multiply by cos. This was another.
No. So
Yeah, it is.
okay. No, remember, oh, here is a triangle.
Cos is what you show you there.
Cosine theta is equal to, this here is theta. Let me put it in red. Let me draw it here. Right, good. So you have a pendulum
Oh,
here.
is it because we find in cosine theta, not just theta, so we don't have to multiply by the.
Yeah, not just
okay,
theta.
okay.
Right, so theta is here. Right, this here is 0.159. This here is 0.6, right? So we can say cosine of theta is equal to, right, adjacent, right? This here would be the opposite. The adjacent 0.159 divided by 0.6, right? This here is the hypotenuse, and divided by 0.6. And then wherever we see cosine theta, we can just sub this in, right? This little thing here, right? Okay, so you can sub that in and then continue solving from there, right? Multiply these two, divide these two, carry over, right? Simplify, you get something like this. Plug it into a calculator, you get 51.83 newtons. Now, what else I'm saying is that if you want to use this other formula, right? The sine formula, you can go ahead and use that as well, right? Just remember, R is going to be equal to 0.6 sine theta, right? And then that's going to cancel out with that. And then you should get something similar. And remember, mass is now 1 kg, right? Mass is 1.4. So keep that in mind as well, if you're going to use the other formula. We should get the same answer. So now do we have those two answers, which is the first part of our question, right? Determine the height of the pendulum and tension in the arm when rotating at 75 reps per minute. Now, the second part, what increasing speed in reps per minute is necessary to reduce the height by 10%. So the height currently is 0.159. Let me switch colors. The height currently is 0.159. Now, a 10% reduction in height would mean we find 10% of this and then we subtract that from it. Well, finding 10% of this and subtracting it from it is the same as 90% of this, right? So if you find 90% of this, that'll be 10% less of what it was originally, right? So we say the new height, the 10% reduction in height, the height that we want to find the velocity for in reps per minute, right, is going to be 90% of the 0.159, right? If that makes sense. So 90%, we know 90% is same as 0.9 times 0.159. Right? Plug this into the calculator, you should get the new height. The new height where we want to find these attributes for is 0.1431 meters, right? Approximately 0.14 meters. Now with this new height, we can plug that into our old formula, right? H is equal to G divided by omega squared. We can plug this new H in, 0.1431. If you want to keep the decimal places, we know gravity again, okay, as 9.81. But what we're gonna have to do to get W is we're gonna have to manipulate this a little bit, right? We're gonna have to carry over the W, bring this over, square root both sides to get rid of this square. And we're gonna end up with something like this, like omega is equal to the square root of G divided by H. Okay, plug 9.81 in and 0.1431. Plug all of this into a calculator. And you should get omega is equal to 8.28 rads per second, right? And that's your velocity. Now we can't stop here. We can't stop here because the question asks, what increasing speed in revolutions per minute is necessary to reduce the height by 10%, right? So we need to convert it back to revolutions per minute. And we also need to note that it's what increase in speed, right? Now, this here is the new speed. New speed. Now, the old speed was 7.854, which is approximately 75 revs per minute, right? It's 75 revs per minute up here, 7.854. So the increasing speed is this new speed minus this old speed, right? The 8.28 rads minus the 7.854. This here is change in speed or increase in speed. Increase in speed. Subtracting those two, we get change in speed is equal to 0.426 rads per second. And of course, we need to convert this, as I said before, to revs per minute, right? Because this is what they asked for, revolutions per minute. So to convert this revolutions per minute, we first need to seconds, right? So seconds to minute multiplied by 60. That's the revolutions. Every 2 pi radians is 1 revolution. So we divide by 2 pi and multiply by 60. The opposite of what we do to convert revs per minute to rads per second. After converting, we should get the increasing speed is equal to 4.07 revs per minute. Okay, good. Now, any questions on this?
Yes, sir. Sir, the new height is 90% of the old height.
Yeah.
Is it in a question or is it
Yeah,
a standard thing?
It is in the
Because
question.
I don't have a question right now.
Good. Okay, good. So,
And next question is, I'm not sure how we get to 7.85.
7.854. Okay, good. So 7.854 comes from here. So we use it at the bottom here. Right, this was the old speed and this is the new speed, right? So let's talk about the old speed first. So where the 7.854 comes from is from converting this 75 revs per minute into rads per second, right? Unit conversion. So determine the height of the pendulum and tension in the arm when rotating at 75 revolutions per minute, right? 75 revolutions per minute. Now, we want to work these questions because things like omega and in formulas where we have the angles and the R's for things to work out neatly, right? We need it in rads per second. Right? We need it in rads per second. So to convert that, we multiply by 2 pi. So 1 revolution is equal to 2 pi radians, right? a complete circle, 1 revolutions. You go around the circle 1 time, you go around 2 pi radians, or 1 revolution. Right? So in order to convert 75 revs per minute into radians, you need to multiply by 2 pi. Now, converting that into rads per second, we multiply by 2 pi, and minutes, right? Minutes, 1 minute is equal to 60 seconds, right? So we need to divide by 60 as well, right? Divide by 60. Plug this into a calculator, you should get 7.854. Okay, 7.854 radians per second. Now this 7.854 is what we use later down in the question here, right? We bring it back. Now back to this new height with this 90%. Let me just make some space. So we calculated the old height with some quick calculations here, right? Use this formula. Some quick calculations. We get height as 0.159. Now, the question asks, what increasing speed in revolutions per minute, we'll look at that later, is necessary to reduce the height by 10%. So to reduce the height by 10%, means that it has to drop to 90%. So let's say this is height, right? Full height. Let's just write as full height. Is supposed to be 100%, right? Now, if you want to reduce this height by 10%, by 10%, we're gonna have to take away 10% of the height, right? So we're gonna be left with 90% of the height. So the new height, or the height, when decreased by 10%, right, with minus 10%, should be equal to 90% of the old height, right? %10 of height, right? So that 10% reduction is the same as just multiplying it by 90%. Alternatively, you can find 10% of the height and then subtract it from the original height, right? But you're gonna get the same answer here. So an easier way is just doing 90% of h, okay? Now, that's just where the 90% comes from, right? You find 90% of h, and then you continue the problem finding the new speed, or the new omega, right? This W thing, you find the new omega. After you find the new omega, you subtract it from the old omega, because they want increase in speed, right? They want increase in speed and not the new speed, right? They want to know how much do we need to increase it by. Well, you need to increase it by 4.07 revs per minute. And along the way, we multiply by 6 and divide by 2 pi, because we're converting from rads per second to revolutions per minute. Okay, good. Does that answer your question?
Yes, sir. Thank you very much.
Okay. Any other questions before I move on? No. All right, good. So now, you guys know that in order to fully understand this topic, you need to work the questions out and see where you might go wrong, see where you might make mistakes, so that you make the mistakes now in class or at home instead of during the test, all right? Because mistakes do happen, so you need to practice. So now for number 23, I want you guys to work it yourself, right? And I want you to think it through. Now, it might be a bit different, but I'm sure you guys can solve it, right? What you need to do is deduce an expression for height of a conical pendulum when rotating at the angular speed of omega rads per second. We've done this before. You guys know how to do this, right? Same as number 1, right? Not number 1, number 19. Now, the arm of a simple conical pendulum is 0.7 meters, and the pendulum bob has a mass of 1.6 kg, right? When the pendulum rotates at 80 revs per minute, determine A, the radius at which the bob rotates, So they want us to find R. Now, we know that R is equal to 1.6 sine theta, right? Or L sine theta. So you can use that along the way to help you out. Right? So determine the radius at which the bob rotates, and B, the tension in the arm, right? So tension, we know how to calculate tension, right? We've been doing that. And of course, the one unique like mass in the arm, just like before. Now for the radius, what you're gonna want to do is just create your triangle, right? Maybe you might have here as 1.6, and somewhere along the way, calculating for tension, you might find height. So you can use the length of this arm along with height to maybe generate some kind of Pythagoras theorem, 1.6 squared minus 8 squared. And that there should give you R, right? The value for R. So work it through, and if you have any issues, let me know. Okay. Take maybe 10, 15 minutes. I don't know. If you have any questions, just ask. All right. Okay, go ahead.
sir.
Yes, someone's saying something.
Yeah, you haven't marked the last tests yet.
No, no.
I had a little mix up because I had actually worked the question. Miss has given us 1.5 kg, and then when I finished the test, then she changed it to 1.5 ton, and I had accidentally sent the 1.5 kg work into you. Eventually, later I sent
So
it.
she changed it in the middle of the test.
Well, I had completed the test by then, but she changed it, yes, and she told us to do it with the
Not
new.
in minutes or almost at the end.
Okay. So what are the two values?
1.5 kg, and then she changed it to 1.5 ton.
Let's see, I don't have the solution.
No, what I'm saying, I send the one like work for 1.5 kg to you, and then I later realized, and then I send the one with 1.5 ton.
Yeah, but a lot of students might make that mistake as well. So I'll make a note of it. Just make a note of it.
It was 0.75 very much, not 1.5.
Or 0.75 then, yeah, something like I can't quite remember the exact figure.
It was 0.75.
Here, tons for
Yes.
the weight of the file.
Yeah, she had
So
given
she-
us a 0.75 kg at first, and then when the test, yeah.
Okay. Okay. Yeah. Good. Okay. No worries. Keep that in mind. Keep that in mind when I mark the test.
I think lots of people got blackout like you too.
Yeah, I know I'm supposed to have another class, so I know if my laptop battery is gonna make it. But yeah, students might be glad to have class canceled.
Yeah, I have blackout too.
I'll see how it goes. Maybe light comes back
So
on. Maybe
almost the
doesn't.
entire country have blackouts, sir.
Yeah, we're running on generator here right now as well at work.
Yeah. Oh, we'll see. I could cancel class for today.
Excuse me, sir. Can you please go up? I want to have the get the formula, sorry, for tension.
Okay. Good. Let me just go all the way up. Give you these two. Maybe meter.
Okay, sir.
Good. Right, these two.
Mhm.
All right, so
Sir.
everyone that's having blackouts and missing parts of the tutorial, I'll upload the video, right? So you can rewatch it on your own time whenever you get power back, right? Don't worry about it. And of course, I will send the handout. So you can just review it on your own time, and you can watch the video if you don't understand any piece. Right?
So we can get the answer for this question too.
Yeah,
the
the answers are right there. 0.74 and 84.3 newtons. Did you get these or not?
I'm finished. Yes.
I got the 3.9 and 0.74.
Mm-hmm. At 0.74 meters for the radius, right?
Yeah, use Pythagoras theorem.
Good. And 84.3.
I got 3.94.
3.94. Seems close enough. Should be fine. Actually.
Sir, I got that same answer too, sir, but when I check back, it's not the working that is needed to find it I used.
Oh, you got 83.9 or whatever too?
Yes, sir, but it's not the way it's supposed to be fine,
Oh,
sir.
so what was your mistake? What was your mistake?
Sir, what I did, sir, I squared the, what's called this thing again, sir? The fancy W thing, sorry.
Omega?
Yes, I squared the omega, sir, then I multiplied it by 9.81. And then the answer I got was 82 point something, and then I add the 1.6 and got 83 point something. So I don't know if the person did the same thing, but I don't think that's the way it's supposed to be fine, sir.
Okay. Let's just pull open Mr. Cell's working. I'd worked it out, but I ain't really able.
So what was the answer? I got 0.74.
Yeah,
Oh yeah, I got that also.
the radius. Right? Yeah, did you guys do this thing? Or did you use the sign? Sign one. You guys use the sign formula.
No, I use the cos.
Okay, and you got 84. The guy that got 83. Is this what you did? Maybe you just had like a slight rounding error.
I did exactly what you have there, 0.14 divided by 0.75.
Okay, good. Then that's correct.
I don't know what
That's correct.
Troy was talking about. Yeah.
Maybe he's talking about something else. He had a mistake. You can alternatively just use t sine theta, right? T sine theta is equal to, can't even remember. T sine theta is equal to mass by acceleration equal to mass omega squared r. So you can plug in your value for r that you just found, or you can do what is the length? The arm 0.75 sine theta, right? And that would cancel out. And then this mass is 1.6. So T should be equal to 1.6 times, this would need to be converted, right? So you'll get some value in here, right? Times 0.75. You need to convert this and put that in there, and then that should give you the 84 as well, right? Okay.
Sir, I heard you ask what I did.
Yeah.
My answer, what I got, sir, is 83.8. And what I did, sir, I multiplied the omega, sir, by the gravity, and then I add the answer that I got. I add 1.6 to my
Why
answer.
did you multiply omega by gravity?
Sir, I don't know. I was trying something.
What
new.
formula were you using? Which one of the formulas?
Sir, to tell you the honest truth, sir, I didn't use any formula. I just decided to punch it on my calculator and see what I would get if I tried, and I got 83.8.
But what was the
83.8.
logic? What was the logic behind it?
Okay, sir. So the logic behind it was find the omega, and then the omega I multiplied that by 9.81, and the answer I add the 1.6, which is the mass to it, and got my 83.8. I don't know where that come from.
Mathematics.
So
But,
that you just kind of using the numbers, multiplying them, and see which one gives you the answer.
I just tried something, sir.
That's not how you do
Because I
it,
did.
Dennis. Don't do that in the test.
I didn't have the formula. That's why I went and asked you back for the formula.
Okay, yeah, don't do that. Don't do that in the test. All right. You can get 5 out of 20. Yeah, and 5 that's just because it won't give you 0. Right. So most of you should get this answer, right? If not, you can look at Mr. Cell's solution, right? It's visible, it's clear, right? So you should follow, right? Right? Good. Now moving on to number 25, and then we call it a day. Very good. So the string of a conical pendulum is 1.25 meters long and can just support a mass of 12 kg without breaking. If the mass of the pendulum bob is 5 kg, determine the radius of the circle described by the bob, and the maximum speed in revolutions per minute that the bob can make without breaking the string. So what's the maximum speed it can go, and the biggest circle that it can describe without breaking the string, right? Now we just learned the string can just only support a mass of 12 kg. If it goes more than 12 kg, it's going to break. So therefore, this string is capable of holding a mass of 12 kg alone. That's its maximum tension. So in this system, right, when spinning this bob around, the maximum tension on the string should be equal to the weight of this 12 kg mass, right? That should make sense logically. So here, the string, 12 kg, right? If you put more than 12 kgs on this thing is gonna break, right? It's gonna break. It's gonna break. So therefore, the maximum tension it can hold is 12 times 9.81, right? Or the weight of 12 kg. 12 kg, right? So max tension is T is equal to 12 times 9.81, which is equal to 117.72 newtons. Now, remember, this is a conical pendulum, and this thing isn't just standing still, right? It's rotating. And the mass isn't exactly 12 kgs, right? It's 5 kgs actually, and it's spinning. But because it's spinning, because there's some force causing it to go around, spin around, that force increases the tension, right? It's not just 5 times 9.81, right? There's more to it, right? There's a horizontal component and a vertical component, right? This here is 5 times 9.81, yeah, but it's also this force affecting it as well, right? Pulling this thing out, right? That's centrifugal force. So we want to know, in the concept of that force, how fast can it go and what's the radius of the circle, okay? So taking this tension into consideration as the max tension we can pull on that rope, right? Substituting that in our formulas, we want to find the things like omega and R, okay? Good. Now first, we're going to find theta. Then we're going to use theta to find R, right? Because remember, R is equal to L sine theta. They gave us L, but we don't know what's theta, right? We want to find R. So we might as well find theta. So in this formula, we know T, we know M, we know G. And looking at it, if we had to choose which formula we're going to use, we're going to look at this one. We're going to say, okay, we don't know T, we don't know theta, we know M, we don't know omega, or do we? No, we don't know omega, and we don't know R. So we have too many unknowns in this one. In this one, we don't know T, or we know T, sorry. We don't know theta, we know M, and we know G. So therefore, we can use theta to find something new, and then use that to find something like R, and then substitute in and work back and find more variables, find more of our unknowns. So this is the formula you want to choose. So T cosine theta is equal to mg. The mass is 5 kgs. That's what it said in the question, right? The mass of the pendulum bob is 5 kgs. Times g, gravitational constant 9.81. Solving for theta, we get theta is equal to cosine inverse of 5 times 9.81, which is 9.05. right? 5 times 9.81 divided by 117.72, right? Plug this into a calculator, you should get theta is equal to 65.376 degrees. Now, having found theta, we can use theta to find our other unknown, which is r. We know r is proportional to the length by means of this trig ratio sine theta. Right? So r is equal to L sine theta. L, the length of that pendulum arm, right? A pendulum arm in this case is a string, which is 1.25 meters long, 1.25. So therefore r is equal to 1.25 sine theta. Theta we just found as 65.376. Again, plug this into a calculator or do it in your head if you can, right? R is equal to 1.136 meters or approximately 1.14 meters. Okay, good, 1.14 meters. Now, T sine theta is equal to m omega squared r. Okay, we still want to find omega, but before we couldn't do that, right? Because we didn't know theta, we didn't know r, and we didn't know omega. We only had t and we only had the mass. But now we got more variables, right? We solved here and we solved here. So now we can put them in and solve for omega, right? Or angular velocity. And the angular velocity in this case is max speed because we're using t as the max tension, right? That 1.17 at 170 newtons. They found up here, right? That max tension, max. So this omega here is max velocity. Okay, good. Now solving this, plug in the value for t. T is 117.72 newtons times sine of theta, where theta is 65.376 degrees, right? Times the mass, which is 5 kgs, omega squared, which is our unknown, times r, which we just found as 1.136, right, meters. Solving this, of course, we're gonna manipulate this algebraically, right? We're gonna multiply this 5 by this 1.136. Then we're gonna carry it over and divide it by that, right? So 5 times 1.136 should give us about 5.68, right? So let's rewrite that back. Over here is equal to 5.68 times omega squared. Omega squared. And that's equal to 117.72 times sine 65.376. This here should be equal to about 107.01, right? Solving for omega, we get omega, right? Remember, carry over, you divide 107.01 divided by 5.68, right? Omega squared here. Square rooting both sides. We get omega is equal to 107 divided by 5.68. Right? So omega is equal to the square root of 107 divided by 5.68, which is equal to 4.34 rads per second. Right? This is in rads per second. The question asks the maximum speed in revolutions per minute. Right? Revolutions per minute. So we need to convert that from rads per second to revolutions per minute. Right? Good. So what we need to do is first multiply by 60, right? To convert seconds to minutes, right? So 4.34 times 60, and then divide that by 2 pi, right? Because 1 revolution is equal to 2 pi, right? Therefore, 1 rad, therefore 1 rad is equal to 1 upon 2 pi revs. Okay. Okay. Any questions on this? Any questions?
No, sir.
So since it's how did you know it's rads per second there?
Well, because we
Was he
because
using
of
degrees?
yeah, well, not because we're using the degrees, because you're gonna find this answer in degrees, but if you put degrees or rads into this function, it's gonna output the same thing. You just when you put rads in, you gotta use the radian version of sine, right? We found this here in degrees because our calculator was set to degrees when we did this, right? When we did this. If our calculator was set to rads, we'd have found this in rads. Now, the reason it's in rads per second is because of the relationship between omega times r is equal to linear velocity, right? Anything involving r, right? In all of these formulas, the basis for them, the only reason they work is because r has this weird relationship, right? Like if you wanted to find the length of an arc using degrees, how would you go about finding that, right? You'd have to do 2 pi r and times that by some fraction, right? Some theta over 360, right? But radians is a very simple way. You just multiply the radians by the r and you get the length of this thing here, right? L, because you can do that with radians. So the reason we get radians is just because these formulas are all based on radians. These formulas weren't calculated using revs per second. Okay?
Thanks. Yep.
When creating these formulas, they weren't thinking about revs, they were thinking about radians. Right? That's it really. Like, yeah. And you can't do this with have this relationship between linear velocity and angular velocity with if this angular velocity is in revs, right? You can't have this relationship, revs per minute. You can't have this relationship. So that's just how the formula, that's what the value spits out. And if you notice, for these formulas, right, we went ahead and convert, right, and put those in. Went ahead and convert and put those in. Okay. Okay, so any other questions? It's a question in the chat. No, sir. All right, good. So this is all I have for you guys. Right. I will email this to you as well. If there are no other questions, you guys can go ahead and leave. Right. Enjoy the rest of your day. It's blackout, but still enjoy the
Same
rest
to
of
you,
your day.
sir.
Nice.
Excuse me, sir. Sir, we coming back for 12?
Well, I don't know because I have blackout, and as you can see, my battery is quite low at the bottom here.
Sir, based on what I've heard, sorry, they said blackout will be on till 3.
Yeah, so I'll send an email out. Maybe cancel class today. Right.
All right, sir.
Okay, that's it. I can leave.